All right. Hi, my name is James Cassidy. I'm a soil science instructor here at Oregon State University, where I teach introductory soil science classes, and I also teach advanced soil management for organic production class. I also teach organic farming and gardening, a class in that. I also run the student farm here on campus. I've been doing that for 22 years or something like that. And I do a lot of talks. And I'm so sorry that I can't actually be with you tonight. But I do have you for the moment. So pay attention. So what we're going to talk about tonight, what am I trying to do here? I got an hour. And what I'm trying to do here is I want to do a little review on soil, which is hard for me to pull in because there's so much I want to tell you about. But a little review on soil so that we can actually talk about what actions you can take to improve your soil and particularly your health of your soil, something called soil health, which I'm sure you're all familiar with and heard a lot about. So I have some tools that I want to show you, some online stuff, some resources. We just don't have that much time, but I would love to come back sometime and do some more with you. So let's just get started. So what is, soil? It's all about soil. I mean, everything is about soil. I mean, I'm not just farming and gardening and stuff, but everything is about soil. I mean, every atom in this room where I am right now, every atom in your body was once has been, what actually, we got to back up a little bit. What soil is, I mean, well, every atom in your body was once inside of a rock. Every atom in this hat was once inside of a rock. And I don't know if you know this, but rocks dissolve in water. Okay, most people don't think about this stuff. Of course, you might. But, here's a rock, right? And look at this thing. And what a rock is a collection of minerals. And that's what the different colors in this rock are. Now, there's different kinds of rocks. I have a bunch of them down here. Look at here. Look at this rock. Look at this rock. These are all different rocks, and they have different minerals. And what are minerals? Minerals are just collections of elements. Like there's 118 different elements in the Earth's in the universe that we know of. 118 elements, and that's what makes up minerals, and different collections of those crystallized form of minerals, which are made of these different elements. That's what rock is. That's what we're all made out of. Every atom in your body is what's once inside of a rock, and rocks dissolve in water. You see that? It just dissolved. I don't know if you're noticing that. Now, it doesn't dissolve very fast because we don't live very long. But when a rock dissolves, if you don't believe me, just take a little bit of sodium chloride. This is table salt, right? A little table salt. That's a lot of table salt. A little table salt. Put it in your hand and lick it. And it just dissolved. It's gone. It dissolved. It went to a liquid phase, right? And the same thing happens with all the minerals in a rock. Now, some minerals dissolve fast, like salts, and some minerals dissolve slow, but they all dissolve, right? And when they dissolve out, they become nutrients. I mean, that's what nutrients are. They are minerals that have dissolved in water, that have been released in an aqueous phase, and then they get taken up by the roots of a plant, incorporated into those tissues, and then you either ate them or your mom ate them, and then that biodegraded in you and became part of the tissues in your body. Every atom in your body has been through the soil system billions of times already. The fact that you are not soil at this moment is a temporary condition. And it's almost over, folks. And I don't mean this talk. I mean, you're just here. You're most of the time you're soil, having a look around, and then you come up and say, hey, this is pretty cool. Before you know it, back to normal. Every atom in your body, sooner or later, is going back to the soil, and pretty soon, actually. So enjoy life. Yeah. So it's a big deal This is really what's happening on the planet. Rocks dissolve in water, which release nutrients that plants use to build their tissues. And then we eat the plants, or we eat animals that eat the plants to build our tissues. And they all die and they go back to the soil. And that's what organic matter is, right? I mean, they're plants and animals that die. Everything that's alive will eventually die, right? Now, there's another thing you need to know to be reminded about soil, and that is about organic matter. I mean, what organic matter is. And I think I have a look. I got a couple of little roses here, right? Dried roses. Look at those things. Aren't they beautiful? And what these are, this is organic matter, right? Here's a leaf. You know, what is this leaf made out of? It's made out of carbon, right? So there's a little mineral nutrients in here, but mostly this is made of carbon. And where did the carbon come from? From a plant? The atmosphere, right? You know, that CO2, this is carbon. There's carbon dioxide in the atmosphere, and plants take it in. They don't breathe it, they eat it. Plants eat plants eat the atmosphere. Okay, they're eating the atmosphere, and they take the carbon dioxide apart, take it apart, and then they put it together into tissues like rose petals, right? And in order for them to do that, requires, it's an endothermic chemical reaction, right? To do that, it's a chemical reaction to take apart CO2 gas and put it together into tissues of wood and leaves and petals, right? That is a chemical reaction. And it's a type of chemical reaction called an endothermic chemical reaction, which means it requires energy input to do it. To take something apart and together, put it together, requires energy input. And where does the energy input come from for plants? The sun, right? The sun. Plants need sunlight energy to do that, right? So the 93 million miles away, there's a ball of fire out there that's giving UV radiation to this planet, and plants have figured out a way to capture that energy and take it and use it to take apart the atmosphere and put it together into these tissues, right? I mean, and that's like, what's so amazing about that is in this leaf right now is the energy of the sun at the time of photosynthesis. The carbon to carbon bonds that are making this leaf actually have the energy of the sunlight that's shown on this plant. And the plant captured that energy in the carbon to carbon bonds. And you know it's there, that energy is there. I'll show you why and how. It's there because if we get this hot enough, it'll burst into flames, right? So like, I have a match right here. Let me get something somewhere. Match. So there. Sorry. There we go. So here is here's a piece of wood. It's called a match. This was once a tree, right? Carbon has been captured from the atmosphere using the energy of the sun. And if I get this to 451 degrees through friction, come on, it bursts into flames. And now look at, it's burning. What is burning? That's an oxidation chemical reaction, and it's releasing the heat energy, right? Yeah, I'm gonna get burned here, right? It's releasing the energy that was in there. That's the sunlight energy. And you notice that it goes away, right? Have you ever noticed when you burn a fire, it goes away? Where is it going to? Back to CO2, water vapor, and heat. And the heat is the energy of the sun at the time of photosynthesis that is captured in the carbon to carbon bonds in the organic matter, right? And plants have figured out a way to capture the energy from the sun to build their tissues, and then they take up mineral. Think about it. What is left in the fireplace after the fire burns out? Ash. What is ash? Ash is the mineral nutrients that dissolved out of the rocks. The carbon went back to CO2. The energy went back as heat left that, and a little bit of water vapor came off because it takes water to make these tissues. And what's left over is the ash. And so think how little ash is actually in the wood compared to the volume of the wood. You can burn wood all night in a fireplace. Just keep putting it in. And 10 hours later, there's a little pile of ash there. And those are the mineral nutrients that are inside. And that's what's in you. I mean, inside of you are mineral nutrients. And if you combust yourself after you die, let's say you decide to be cremated, what's left over? Ash. And where did the rest of the body go? CO2, water vapor, and heat. And that's what it's all about. I mean, there's a ball of fire giving UV radiation to this planet. Plants have figured out a way to do that. And they capture the energy and they live in soil. And the soil, the roots are where they get the mineral nutrients. And the top and the above ground part is where they get the energy and the carbon. And that's what a plant is. It's almost like we live in a giant solar system. You know what I mean? Wow, we do. We live in a giant solar system. And that's what soil is. Soil is rotted rocks and accumulated decomposed organic matter. And that organic matter has energy in it. Now, maybe you don't know this. Maybe you do. But in a single pinch of soil, here's some soil. Look at that stuff. In a single pinch of soil, there are over 1 billion living organisms in there right now. And in this pinch too, 1 billion living organisms in there, representing tens of thousands of species. And most of them, we don't even know who they are or what they do, but they're there. And they're doing important stuff. You know what they're doing? They're biodegrading the organic matter and releasing the nutrients from it. And they're eating the organic matter. That's what you do 3 times. You want to know what the answer is? Doesn't matter what the question is. Do you want to know what the answer is? The answer is add organic matter. Everybody just say it. Add organic matter. What's the answer? Add organic matter. Because when you add organic matter, you're adding carbon and energy to the soil. And the billions in a single pinch, they need to eat organic matter. And the more organic matter you put in the soil, the more biologically active the soil is. The more biologically active the soil is, the more efficient it is at releasing those nutrients and that energy to do work to build other plants. And the more plants that are grown, the better the soil is at growing plants. And the better the soil is at growing plants, the more plants there are. And the more plants there are, the better it is at growing plants. You see what I'm saying? That's called soil building. And that's what soil health is all about. Soil health is about accumulating organic matter in the soil. And the easiest way to do that is to grow plants and leave behind. That's what a cover crop is. Cover crops are crops that you leave, that you grow specifically to feed back to the soil. But it's not just organic matter. Cover crops also put roots into the ground and they punch holes down into the ground. Think about it. When a tiny little root goes down, tiny little root here, goes down into the soil, and then it gets bigger, and then it gets bigger. And as it grows, because it's accumulating carbon and energy, as it gets bigger, it makes a bigger hole in the soil. And then what happens in the fireplace? When you burn the organic matter, it goes back to CO2, water vapor, and heat, and it leaves behind mineral ash. And what happens to this rose? If I were to bury this in soil, it would go away and it would become CO2, water vapor, heat, and ash. And that's called rotting, decomposition. And that's done by the billions of organisms in a single pinch. And you might be saying, okay, so that's like burning. It's exactly like burning, except one thing. The bugs, the billions in a single pinch that are in my finger right now, the little bacteria and the fungi, what they do is they ooze out enzymes, right? Enzymes are chemicals that are catalysts, and they're catalysts that make the oxidation reaction that we call burning happen at a lower temperature. So it's like rotting and it takes water and chemicals to do that. It burns at a lower temperature. In fact, it burns at a temperature of about, let's see, 97 degrees. Like in you right now, you eat food to get the carbon, the energy, and the mineral nutrients. And it doesn't have to be 451 degrees for that oxidation to happen, because you have the same bugs that are in the soil are in your gut right now. And you're adding organic matter. They're oozing out enzymes. They're lowering the activation energy necessary for the oxidation reaction called burning to happen. And how do you get a fire to burn hotter? Oxygen in. And what comes off of a fire after it burns? CO2, water vapor, and heat. Everybody, let's do this together. Come on, let's just do this. Oxygen in, CO2, water vapor, and heat out. It's like a fire inside of you. And that's what's happening in the soil. The same thing. The billions in a single pinch are eating the organic matter. They're using oxygen to do it. They're breaking those chemical bonds. They're getting the mineral nutrients, and they're getting the energy from the sun. And then they move their little arms or their little legs or their little antennas. And every time they do that, a little bit of heat is given off that originally came from the sun. That's what soil is. Soil is a battery that stores energy from the sun for the billions of organisms to do their work to build plants. Soil is a battery that stores energy in the form of organic matter. The chemical bonds, the carbon to carbon bonds are actually whole. And that's what, I mean, see this, look, I can do this. You know what that is? That's energy from the sun. Every time you blink your eyes, that's energy from the sun. That is, now you get warm. I'm getting warm. Just what warm? What is warm? Warm is the energy of the sun that you ate the food. You see how it works? That's what soil is. Everything else is a sideshow. Nothing else is real. It's look at that. Oh, real. That's really awesome. Anyway, so all right. So all that is real is that there's a ball of fire out there 93 million miles away giving UV radiation to this planet. Plants have figured out a way to capture their energy and to make chemical bonds, and they live in soil, and then they die, and that organic matter goes back to the soil, and the billions in a single pinch eat all the organic matter and release the mineral nutrients and the energy and the carbon. And that's it. Everything else is a fantasy. So I'm going to go to some slides. I'm going to talk about a few things, and then I'm going to show you some really important stuff. All right. So first of all, let's just get to my slides of my show. I'm not going to spend a lot of time on these because we don't have a lot of time. And I also want to take your questions because I think I could actually answer, or I could address your specific needs live better than trying to anticipate what they are. So this is just a quick talk. So it's all about soil. You got that? That's what that whole part of this talk was. I just did it. And check it out. There's different kinds of soil. Soil, remember, there's 20,000 different named soils. 20,000. And they all belong to one of the 12 soil orders. Now look at the one on the left here. It's called an aridisol. You know what that means? It means dry. Do rocks dissolve in air? No, they dissolve in water. So this soil is very dry. So there's not a lot of nutrients being released. And they're very thin soils. And there's not a lot of organic matter because there's not a lot of water, and because there's not a lot of mineral nutrients, because it isn't a lot of water. And look over here on the right, this is called a mollisol. And there's thousands of different kinds of iridisols and mollisols, right? Or hundreds. But look at this on the right. This is in feet. Look how dark this is, down to 2 feet. I mean, this image of this is like soil porn or something. If you're a farmer, you look at that soil on the right and you're going, wow, that looks like money, and money looks like boats and fun. Okay. All right. So, and look at how dark it is. You know why it's dark? What is that darkness from? It's from organic matter. And this soil adds its own organic matter by growing it in the form of roots in grasses. And it did that for 20 million years. And it became a mollisol. The bison on the plain eating the grass and pooping out, and the grasses went deeper, and eating them stimulated them to grow faster and pushing more carbon and energy down into the roots, by the roots into the roots, and then they die and go away, and a little bit of organic matter is left behind, and there's more biological activity in this than there is over here. And that's the difference between survival and not on the planet, is the soil. It's all about soil. I mean, you look at this. Here's another soil on the right here. I mean, 2/3 of the earth, rather 1/3 of the Earth's ice-free surface looks like these two soils. Now this one, it's a little dark in here, but look, if you want to farm this, you got to dig all these rocks out first. And once you dig all those rocks out, there's not much left. So that's 1/3 of the Earth's ice-free surface are these two soils. And if you look at look at here's the soils of the world. Look at mollisols, that dark one. 21% of the United States land is mollisols. And worldwide 7%. I mean, that's why we're here talking on Zoom right now about you farming and learning more about soil electronically. I mean, all of that is because we have the good soil. They who have the good soil have the technology. I mean, they who have the good soil had the good agriculture, and the good agriculture led to the good industrial revolution, which led to the technological revolution, right? And all this stuff. And that doesn't happen where the iridosols are. Here, these are the troubled parts. And this is what you're looking at here is a map of political power. But I'm not going to go on and on about that. It's fascinating. But I want to get to the stuff you want to think about. I want you to think about the larger picture of what soil is. Soil determines every action you will ever do in your life, where you live, how you live, and why you live the way you do is because of the soil in your nation, in your state, under your feet. All right. So, we have 10 of the 12 soil orders right here in Oregon. We got spotosols on the coast and andisols in the Cascades. We've got entisols down by the rivers where they're constantly flooding. And the inceptisols are the ones that are a little further away from the river. Look, here's real soil. Soil doesn't come in a bag. Soil forms over time when rocks dissolve and release nutrients. And when plants live there and die, live and die, and live and die, and leave behind organic matter, and the billions in a single pinch are being fed by the energy of the sun, the carbon from the atmosphere, and the mineral nutrients and water. And that's what soil is. Soil doesn't come in a bag, right? Bottom line, soil is habitat. If you get nothing else out of this talk tonight, soil is habitat. By any measure, the most diverse habitat on the planet Earth is the soil itself. And look at the holes in this soil. Just for a second here. Look at this. Stop sharing. I want you to look at all those holes. You see the holes in that soil, those macropores? That's what you want. You're managing soil for macro porosity, meaning large pores. Why is there a large hole? Where do these large pores come from? Old roots and burrowing animals and worms. And what do? They went in there and they got bigger and they pushed the soil apart using the energy of the sun to do so, push it apart, and then they died and they went back to CO2, water vapor, heat, and a little bit of ash was left. And you can see that that's the castings of former life forms that are no longer alive. And yet they sculpted the soil to have larger pores. And the reason you want large pores, because sure, there's plenty of small pores because there's different size particles, sand, silt, and clay. But to make a pore that big has to be a big root. And you know what? Large pores drain under the force of gravity and they pull water in because of the force of gravity. And that's what it causes good aeration and drainage. Because once the water drains out, it pulls in oxygen. As the water drains from the soil is breathing. And you know what? Plants need water all the time. Plants need oxygen at their roots all the time. And that's why you want a well-drained soil. And how do you do that? You grow a cover crop that makes larger pores so the water can drain and go deeper and be stored deeper and very deep in the soil. Look, water, take a bath sometime, please. Small pores hold water against the force of gravity. You see that little bridge of water there? Yeah, a little bridge of water. That bridge of water is being held there by capillary force. Small pores hold water against the force of gravity. Large pores drain under the force of gravity. And what you want in your soil are large pores, medium pores, small pores, and super tiny pores, because the large pores have the air in them and the small pores hold the water. And when do plants need air and water? All the time at their roots. And that's what soil health is well oxygenated, water-rich environments that have air-filled pores and water-filled pores. And that's what the billions in a single pinch need, just like you do. You need to live in a giant air-filled pore, but you also need water, right? To drink. And that's what plants need. They need air and water. You need air and water. You need carbon and energy. You need organic matter. You need to eat organic matter 3 times a day. You do that. And why? So you can live, so that the mineral nutrients are in you and the energy allows you to blink your eyes and to think and to wonder about the world. Yeah, soil. Yeah, it's all about soil. And soil health is all about preserving the habitat. Soil is habitat. And you're not really farming. You're ranching microbes. You're not even really ranching microbes. You're managing space. The space, the different size pores are different size habitats that are either air-filled or water-filled. And the more diverse the pore size distribution is, the more diverse the habitat is. The more diverse the habitat is, the more diverse the organisms are. The more diverse the organisms are, the more diverse the function of the soil is. The more diverse the function of the soil is, the more efficient it is at processing carbon, energy, and nutrients to release more carbon, energy, and nutrients for the next generation of plants. And the next generation of plants push down their roots and make large pores, which make the pore size diversity wider. Think about it. Pull up a plant and look at the different size roots. Those are sculpting the soil in a favorable manner so that when they die, they leave behind a pore size distribution that is favorable for the next generation of plants. And over time, you have a well-structured soil that is better for accumulating energy from the sun and carbon from the atmosphere in the form of plants that feeds the billions in a single pit. That's what it is. That's what it is. All right, I'll go back to my slides, if you don't mind. Soil is habitat, right? That's what I want you to remember. And once you understand all of that, you know what to do to it and what not to do to it. You don't need me to tell you exactly what to do. You need to just understand what it is. And you can figure out the rest, right? So look, here's a tiny piece of soil. Look what's in there. There's big pores that are drained and there's small pores that hold water. And look, these are aquatic organisms here. And here's an organism that is not an aquatic organism. And you need them both. In fact, this is an entire ecosystem in a piece of soil that's about that big. See that tiny little piece? That's about how big this little piece of this drawing is. And in there is all of this life. And you know what they're doing? They're processing chemicals, energy, they're processing carbon, energy, and nutrients, and they're making it available to the plant. Look, here's the root that's taking it up. Here's a fungi that has a mycorrhizal association with the root, and it allows it to actually get more mineral nutrients in exchange for the energy from the sun. I mean, fungi don't photosynthesize. You know what they do? They either eat dead stuff or they form relationships with living things that give them the chemical energy in the form of sugar water. And that's what mycorrhizae are. And all of this diversity of organisms is because of the diversity of habitat and the minimizing of disturbance. And that is the job, folks, is minimizing disturbance as much as possible and still do agriculture, but minimizing disturbance, because when you disturb the soil, you break up all of this sculpted habitat. And it takes time to create this diverse habitat. And that's why you grow cover crops. And that's why you try and do minimum or no-till agriculture, is to preserve the structure of the soil because it's better habitat. Bottom line, soil is a living thing. It's not a chemical sponge. It is a living thing. And your job is to enhance that or protect it. And it's extremely resilient. I mean, you can hit it pretty hard and soil bounces back for a while, for like 100 years maybe. And then all of a sudden the house of cards comes down and the biology crashes. And once the biology crashes, there is no cycling of chemical energy, nutrients, and all that stuff. So you just want to like minimize disturbance, add organic matter, and let the laws of thermodynamics take it the rest of the way. So soil is rotted rocks and decomposed organic matter. It's about half space, and a rock dissolves in water and releases nutrients and becomes different size particles of sand, silt, and clay. Okay, clay is a special thing called a secondary mineral that forms when primary minerals, meaning rocks like this, when they dissolve, they recrystallize at the surface of the earth. This can dissolve and then recrystallize into something called clay. Clay is a different thing. It's not just a rock. It's a secondary mineral that's formed when rocks dissolve in water and recrystallize. And when that happens, look what's released. Look, silica, aluminum. Those are magnesium, potassium. Those are nutrients that are dissolved out of primary rocks. And some of these minerals actually form secondary minerals called clay, which are sheets of silica and aluminum oxide. And I'm going to go really fast on this. But this is what dissolves out of a rock: silica tetrahedrons and aluminum octahedrons, and they form these sheets, and they're really small and they have giant surface area. And when those, as it turns out, there's also substitution that happens in that crystalline sheet that forms a net negative charge on that sheet. So clay is a very, 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 very tiny layered high surface area thing that has a negative charge on it. And you know what sticks to negatively charged things? Positively charged things. And you know what the charge on most mineral nutrients that you need in your body? Positively charged. So a positively charged nutrient that dissolves out of the rock sticks temporarily onto clay. And that's what the cation exchange capacity of the clay is the soil. You get a soil test and you look at the percent organic matter, and you look at the percent sand, silt, clay, but you look at the clay and you find out what the cation exchange capacity of that soil is. And that is the ability, the number of negative charges per kilogram of dry soil is the cation exchange capacity. That's what cation, so that number, the higher that number is, the more nutrients it can store. The more nutrients it can store, the more plants it can grow and capture more energy from the sun and more carbon from the atmosphere. And that's what soil is. And here's the dirty little secret. Other than clay, there's one other thing in soil that has as much negative charge as the best clay, and that is organic matter itself. Organic matter itself increases the cation exchange capacity of the soil, so it can capture more energy and carbon. and make more organic matter and accumulate more organic matter. So there's more cation exchange capacity. So it can grow more plants, which makes for more organic. See how that works? That's what soil building is. And that's what you need to just do. You just need to help it do that. It does it on its own. I mean, there was a time before us, and the soil rules. The soil still rules. You know what? Everything is as it should be in the soil. I don't care what you're worried about today and what you're worried about for tomorrow. But in the soil, everything is as it should be, and it will be, with or without us. It's just a matter of whether we want to be here or not. And this is the truth. This is what we need to think about. You know, don't think about all the other crap. Think about this and grow cover crops, add organic matter, put compost on. What is compost? Decomposed organic matter that has, remember, you know how compost goes away, right? Compost piles get smaller, just like fires get smaller, the wood gets smaller because it goes back to CO2, water vapor. You see the steam, water vapor, heat, that's why it's hot, it's the energy of the sun. And in the end, what's left over? A bunch of ash. So compost is decomposed organic matter that's in a stable form that has higher levels of ash in it, mineral nutrients, and that's why you use it on the farm. So adding compost adds mineral nutrients and energy from the sun and billions in a single pinch biota. Growing, but cover crops do something that compost can't. Cover crops push roots into the ground and then they die. And they push it into the ground and they keep doing that over and over and over. And they leave behind large holes, right? Compost doesn't do that. Now worms do and bugs do that eat the compost. So that's why you add compost, and that's why you grow cover crops. And that's why you minimize disturbance and leave crop residues. And the reason you want to do all of that, you want to do that so you end up with I'll show you really quickly. I'm going to take you to slide 72. Here it is. I mean, look at this. This is nice. The difference between poorly aggregated soil that's been compacted and very nicely aggregated soil, because look at that, because it's darker, because it has more organic matter. It has more carbon, energy, and nutrients. It has more biota in it. It's got large pores, medium pores, and small pores, right? And look at that, there's an earthworm in there, right? So that's, you know, the basics of it. And what you're trying to prevent is erosion, really, because when soils erode, you lose the clay first. When you see dirty water running down a stream, that's the clay. And you know what clay is? Clay is a secondary mineral. It has a negative charge. It can store nutrients. So when you have erosion, you're losing the cation exchange capacity, which allows the soil to grow and to build. And when you start losing that, you're going the other way. And so what you want are soils that are high in organic matter. And when they get wet, they still have large macropores and drain. Where here's a soil that's low in organic matter. Once it's wet, all the macroporosity just falls away, and that's all that, and you don't have the air anymore, and they become anaerobic. And wet, cold soils don't germinate seeds very well. In fact, wet, cold soils are good habitat for most diseases of plants, because plants are at their weakest when they're cold and wet. And diseases have adapted to living under those conditions because the plant's defense mechanisms are lowered, and that's why they attack them. And that's why your pumpkins at the end of the season get powdery mildew, because the fungi don't mind it being cold and wet, and the plant is kind of like dying, and then they just eat it. And you know why the disease is eating it? Just to get the carbon and the energy and the mineral nutrients, just like you, right? So let's talk about erosion really quickly. And then I'm going to show you some cool stuff. I mean, I think this is all cool, but I'm going to show you some tools. So really quickly, erosion is, and this is probably surprising to most people, is erosion is initiated by the impact of the raindrop. It's initiated by the impact of the raindrop. And when that happens, that it doesn't seem like a lot of energy, but on bare soil, a large raindrop can go about 20 kilometers an hour. And when it hits the ground, it actually explodes out air and it actually detaches particles. And you know which particles are detached the easiest? The clays, the small ones, and the organic matter, the lightweight stuff, the stuff that floats. And those are the two things that have the negative charge. And when they get detached, and then the flowing water is what takes it away. But it's the impact of the raindrop that actually detaches the particles. So if you can just have a little bit of ground cover, even 10%, think about this, 10% cover of some sort of plants growing or some sort of mulch, 10% reduces the erosion rate by 50%. And if you can have 50% cover over the bare soil, you get a 90% reduction in erosion, because a little piece of leaf that's sitting on the soil surface takes up that impact of the raindrop. Or it hits a leaf first and then it drips another 6 inches and it doesn't have the impact power. So you want to minimize disturbance. You want to maximize the amount of organic matter. You want to grow cover crops. You want to minimize tillage. And you also want to leave cover. And that's another function of cover crops, is that they protect against these erosion mechanics. All right. So I want to show you a couple of things because I know we're running out of time here. And first thing I want to show you is this fabulous book. Let me see. I'll share this with you. Let's see, where is that? Is that? Yeah, there's this book and it's free online, and it's called Managing Cover Crops Profitably. Pause this and write this down. And it's by the Sustainable Agriculture Research and Education Foundation. And you can get a paper copy for 20 bucks, but there's a PDF of it right here. And I gotta show this to you. If you just download it, here it is. There's the book. It's free. It's an awesome book. And if you go to page 69, oh, it's such a good book. I mean, it's fascinating. Let me show you the table of contents. And the way it works is there's all the stuff we've been talking about is well laid out here, and about conservation, tillage, and crop rotations, and managing pests with cover crops, and building soil fertility with cover crops. And then there's a set of charts I want to show you. And then there's all the different cover crops they talk about here. There's actual cultural information about how to grow them, how to terminate them, and what their functions are. But you got to see this. These charts right here. Look at this. So here's some non-legumes, and so here's some brassicas, and here's some legumes that you can grow as cover crops. And here's the darker this little circle is, the better they are at the characteristics. So here's legumes as a nitrogen source. The ones, the dark circles are the ones that are better than these. And then look at the total pounds of nitrogen per acre that you can expect. Well, look at, here's the pounds of dry matter per acre. Look, whether they're a nitrogen scavenger or a soil builder or an erosion fighter or a weed fighter or good for grazing or quick growth. And that's just chart number 2. Look at chart number 3. Here's the performance and roles, whether they have a long lasting residue or whether they have a good harvest value or whether a good cash crop for interseeding, and other comments. Look at this one. Here's the cultural traits of the same cover crops. Different names of them. Here's their hardiness zone. Here's their tolerances. Look at these. The tolerances of heat and drought and shade and flood and low fertility, and whether they have an upright or what their growth habit is like, what pHs are like, when they're best established, what season. And look at this. Here's the seeding rates, whether you drill them or broadcast them. Here's the approximate cost. You know, this book is maybe 5-10 years old, so who knows if these are perfect, but they're relative costs. And And all of these, check this one out. Here's the potential advantages and disadvantage of those 10 cover crops. And they're related cover crops, right? So you can look up different things. Here's whether they're good for nematodes, or they help with disease, or they have allelopathic characteristics, or whether they're good at choking weeds, or they attract beneficials, or they're good at bearing traffic, etc. I mean, all of that's in this book, and it's free. Look, here's more. Here's the potential disadvantages, whether there's a pest risk, whether they can become weedy, or whether they harbor crop diseases, or some of the management challenges. And you go elsewhere in this book, and you can just look up, like, here's information about, let's just say what this crop is. Here's here's field peas and where they grow and the benefits of them, and whether they're quick growing, or they can be, or they're chilled, or how you manage them, how you plant them, and all the stuff, how you kill them, and how you incorporate them, and what their potential advantages and disadvantages, detailed information. There's something you really should get, okay? If you want to know about, and because different cover crops have different properties that do different functions. Do you want to get nitrogen? Do you want to add organic matter? Do you want to have roots that go really deep and pull nutrients up? Or do you want cover crops that punch through paw pads? Or do you want ones that attract beneficials? Or do you want ones that fight weeds? Or do you want cover crops that are really good at erosion fighting? See? And different crops do different functions. Different cover crops do. And that's why you want to get this book. Another thing I want to show you is, let's see. Oh yeah, there's this, stop sharing here. Get to that. Here, check this out. This is the California Soil Resource Network. And this is a really powerful thing. Where is it? And you just Google California Soil Resource Lab. You go there and you go to the soil web apps. Okay, I'll back that out. So you go to the California Soil Resource Lab. Here's the homepage. You go to soil web apps, and there's an app for your phone that you should pause this video right now, go to the app store and find Soil Web. It's an app, and here it is. It's called Soil Web. And what it does is you just get soil data, and wherever you're standing, it'll tell you what soil is under your feet that have been mapped in the United States. The 20,000 different named soils. Look at, here it comes. Look, under my feet right now is Dayton Amity. Those are two different soil types. Those are two of 20,000 different soils. And I can look up the percent organic matter. I can look up the depth at which the clay accumulates more. I can look at the pH at depth. Okay, and I'm going to show you. And there's a plugin for your Google Earth called the Soil Web Earth, and you click on that. And you just see this little thing down here? This is a little program, and you click on that, and it opens it. Oh no! I hope it's going to work out here. Is that going to work? There it is. And it automatically loads it into your Google Earth. And then you're like, what is this talking? And there it is. Look at off on the left here. You see Soil Web. So now there's a layer of soils, all the soils. And so now if I go to the student farm, which is in Corvallis, Oregon, and I zoom to that on my Google Earth, and all of the 20,000 different soils that have been described are now on Google Earth. And here's where the student farm is, just so you know where it is. Here's our Corvallis. Across the river, this is the East Farm Research Station for Oregon State University. And look at, to see the lines in this region right here, this is Camas, which is one of 20,000 different soils. And if I click on anything blue, and look, there's Camas, and there's what it looks like. Look, there's the organic matter rich surface soils. And right, and there's all this other stuff like the land capability class for irrigated and non-irrigated, the ecological site description. Here's the erosion factor. Here's the types of things that the wildlife associations. Here's the hydric rating. Here's the plant available water. Here's the parent materials made from recent sandy and gravelly alluvium derived from mixed sources because it's floods. And it has a low water holding capacity because look how much it's got, very little clay and it's a lot of sand. Look at these up close. These are our graphs at depth. And this is all on your phone too, okay? And look at here at the surface, it's about 69% sand. And you go down about 38 centimeters and it's 91% sand. And look at the clay is only 8% and it goes down to about 3%. And that's why there's not very much water holding capacity because it's mostly sand. Look at the pH is about 6.5 all the way down, right? Here's a percent organic matter. It's only 2% organic matter. 4% organic matter is great. If you get a soil test and you have 4% organic matter, you're doing it right. And if every year that you test your soil and look at the organic matter, it's still holding at 4% or going up a little bit, you're doing it right. If you notice that you have low organic matter, you got to build organic matter because organic matter is carbon, energy, and nutrients and food for the billions in a single pinch. And they make the soil so that you can grow more crops, so that you can have a super nice sailboat. See what I'm saying? How it works? Because soil is it's about producing things of value, and everything flows from agriculture. It all flows from agriculture. So you're already doing the cool stuff. You are the basis of the economy, and the basis of your work is the soil, right? So there's a tool called, it's a plugin for Google Earth, and you can get that. And we can talk about this in the questions. We can actually look at your farm and we could just discuss it. You know, wouldn't that be fun? So maybe that's what we'll do in the question and answer. I just got a couple more things I want to show you. Let's see if I can get to, I think the one thing I really wanted to show you before we go is this. Well, first this. So here, oh dang, what happened? What happened? Hang on. I'm actually doing a lot of stuff here, believe it or not. Okay, let's hope this works. Okay, so again, find out more about your soil. Get the soil plugin for Google Earth from the California Soil Resource Laboratory, the Soil Web Earth app that automatically loads into your Google Earth if you have it. If you don't have Google Earth, they have another app there that you can just right on their website, and you can put in your address and it'll take you to your soil and you can look at it. And you know, I run the student farm. I teach this for a living. I am teaching the next generation, the young kids who are inheriting this problematic earth that we've left them. They are excited. They want to do agriculture and they want to build the soil. And that's my job. My job is to get them jazzed about it. And believe me, I get them jazzed about it. They love it. They're soil maniacs. So to help, would you please go to soilforward.org and buy one of these shirts? I mean, buy one of these shirts. I have them in ladies and I also have them in gender neutral. And 100% of the proceeds from this t-shirt go to fund my student farm internship program. We receive very little support from the university. They let us use the land, but we don't get any economic support. And all of our funding is self-funded through the sale of fruit and vegetables and t-shirts. So won't you please go to soilforward.org right now and buy a t-shirt that means something. Soil. It's all about soil. And you wear this shirt, let me tell you, you wear this shirt and people are going to say, people who know about soil, who know about the student farm are going to scream, soil, at you. Just mark my words. Just saying. You're going to wear this shirt and you're going to hear soil. And you go, yeah, soil. And I also have them in Klingon and in Vulcan. You know, which side of the bed are you getting up on in the morning? Klingon or Vulcan? Klingon or Vulcan? Or soil? It's all about soil, folks. Please, won't you support student farming at Oregon State University? Support my program, the OSU Organic Growers Club, right? That's what we're called, the OSU Organic Growers Club. And if you go to soilforward.org, you can see the vegetables that we're selling there. And if you don't want a t-shirt, just donate. You know, oh, I have one more thing. I also sell on that site this bumper sticker. Yeah, put that on the back here. It might be the only reason to have a car is for this bumper sticker, okay? Start seeing soil, won't you? Soil, it's what it's all about. All right. Happy to take your questions. Thank you for your attention.